So, as we said, for the name and surname, nothing is different for the labs. It's an array of 5 elements. So, either you push a scanf with 5% Ds in here, or you construct a for loop that does the scanf. Into lab I. But we need the address of it. So this, but I know you are professionals and you will not do this childish but simple representation. You will prefer instead of this lab plus I. Right? This is equal to this. Work it out in pointer algebra and you will come to it. The same applies for this, etc., etc. There is ways to initialize the structure the moment you cut it, the moment you create it. Here, to some default values, you can do this, but it is not much useful. You use this curly brace representation, not so important, less used, go and read it from your book. But the important thing that you have understand and digest is you cannot use the initializer in your executive statements. So, despite our all wishes and expectations expectations are in that direction, you cannot do something like this. Best student is equal to curly brace name Ali. And he got a 60 and 49, etc. This is unfortunately not allowed. No, you cannot do this. Okay, so what can we do then with structures? Lots of things, but before that, I want to explain how the memory organization is done for structures. In our case, for example, best student has each one is a child type, short integers, and goes on like that. Then, following this, starts surname. The name of this is name 0, name 9, and then child surname then integers, presumably a bigger size stuff for midterm, and another integer, final, and then 5 integers for lab, 5 integers, and plus 3 integers. So what is the whole size of it? It is the sum over all subfields, sub size of subfield. Yeah. Which is not always correct. So the correct information is size of structure student is greater or equal to subfield. Why is this so? This has nothing to do with computer science. It has nothing to do with the C language itself. It boils down to the need of some processes. Some processes need some of the data to be sitting on even or double even. That means modulo 4 equals 0 addresses. This has no reason beyond electronics, right? Some electronical design requires this. Therefore, compiler knows about the architecture it is compiling for. So when there is, let's say, an integer sitting in a place where it cannot pick it from CPU-wise, then it inserts here some extra bytes. These bytes are usually varying from 0 to 3 and are called alignment bytes. Alignment bytes. Possible alignment bytes. They are not used to store any information. They are just there to align this integer at a specific address property. Let's say even addresses or double even addresses. Therefore, the size of the structure can be slightly bigger than the sum of the sizes of its subfields. This is possible, quite common, especially on the Intel architecture CPUs. Don't get shocked when you observe this. It's a known, common phenomenon. Okay, but what C guarantees us is that the position of name is before surname, and midterm is before final, and midterm is after surname. This order is strictly obeyed. This is something new to you. when we do in, let's say, in the global environment, a declaration of two variables, let's say a and float f, right? It is a misconception to assume that a comes in the memory before f. This is not true. You don't know this. Yes, maybe 90% of the compilers would do this, but the compiler has this freedom to put f above a in the memory. It can do this. You cannot assume that they are following each other. You cannot assume that they are adjacent to each other. No, you cannot do this. But when it comes to structure, yes, you can. The only minor deficiency is that due to the hardware requirements, maybe there would be an alignment between surname and midterm, let's say 1 or 2 or 3 bytes in here, blank, unused bytes, but certainly surname will be above midterm. Why I'm emphasizing this so much, we will make use of this later. We will use it to our benefit. Okay. Now, let's do a very simple example that makes use of structures right away, right now. Let me get lapis pencil. Slowly. Yep. Remember complex numbers. Yes, you could do it with arrays, but at every time you have to create an array and copy it down. Big stuff. Interestingly, structures are first-class member of the language, so we don't need them. Let's define a complex number. Structure, complex. Now, how many fields do we have? 2 fields. We have names for them. The real part and the imaginary part. Let's abbreviate as imaginary. Yes, I could have written it as float real, float imaginary, but I'm a lazy person. Right? Please note that normally we have the right to put in here a variable, but for this moment I don't do it. You don't do it too, right? Now let's write a function that adds, for example, 2 complex numbers. So just give a name, complex add. What does it return? A complex number added to another complex number is a complex number. So it's, in our case, a struct complex. Yeah. Then struct complex first number. Let's say, just give it a name. What shall I give it? Yeah, okay, Z. Z1. And the second number, in the arguments I cannot just continue with the identifiers. I have to put the type as well, so once more. Structure complex Z2. Now, we need a way to access the return box. We don't have it. That is a deficiency of C. In contrary to Pascal, which gives you a way to access the return box, C does not. The only way is the return statement, return something, which then gets copied into the return value box. So unfortunately, we create a temporary value structure, but complex result. Okay, now we are ready to take off result. The result's real part is a floating point, which is obtained by Z1 real plus Z2. If it would be a multiplication, it would be more complicated, you know that. Okay, so the result fields are computed and stored. Now time to fly back. Yes, this does it. How many times have I had to write structures? 1, 2, 3, 4. That doesn't stop, does it? But anyway, that is the way. Now, a very natural expectation is that if, let's say, in the global variable section or in a local, I have two variables, let's say, structure, complex, A and B, right? Or let's call it X and Y. X and Y. Now I want to add these, well, to get a result in Z. I have to call this function, no other way. Complex add, complex add X and Y to, here of course goes in some initialization and values, etc. if you want to build a proper complex algebra, then you write it for multiplication, subtraction, and division. No, you don't stop there. Also converting a real number to a complex number, which has the imaginary part as 0. A function which tests whether a number is, the resulting value has boiled down to be a real number, so maybe a complex to real, etc., etc. Is there a way to construct all the algebra by making use of the nice infix operators, plus and minus, multiplication sign? So somehow can I connect this defined function to the plus operator? So instead of this, I could have very nicely written this. Z is equal x plus y, where x is a structure, y is another structure. Can I do this? The plain answer in vain is no. Not in C. In C++, you can do this by replacing this with the keyword operator plus, and you can define this. You cannot change the priorities, but anyway, you can extend the computational domain to include complex structures. In C, you cannot. You cannot also get something which says printf, let's say %x standing for complex, Z. You don't have this. You cannot extend the function's abilities to do something. You have to write your own printf, complex printf. So, honestly, structures are something very nice, but not taken to their full extent. There is a narrow coming, which was corrected in C++. Okay. Now, in our following lecture, we will be talking about a more professional way to handle structures. Now, a short break.